Okay, thanks, Joe, for letting me talk about this. Part of the idea of the title is to be extremely provocative. What I'm really going to show you is some hard calculations, and on top of that, I'm going to put an interpretation. The interpretation you can, in some sense, think is the thing that lets you talk about firewalls. The rest is honest. So let me tell you a few things that are my opinion. How can we actually do an experiment on firewalls? I mean, in a certain sense, this is what we would want. And I don't mean a Gedanken experiment. I mean really throw someone into a black hole. But if you want to do it via calculation, what you, in some sense, want is what I would call a microscopic theory of geometry. So we are always talking about semi-classical or classical gravity, and we don't understand how a geometry breaks down or what is really a horizon. I think we're going to have a very hard time figuring this mess out. So if you have a microscopic theory of geometry, then we need to identify what's a horizon, and then it's up to us. And then you have to calculate what happens. So this is my prescription for how we should deal with this. And let me tell you a bit about what firewalls do. They detail a time-dependent experiment. You throw someone into a black hole. Right now, Joe is not a candidate because he believes he'll burn up to a crisp. And ask what happens as time goes by and they cross the horizon. So this is really what the firewall experiment is. You just let someone cross a horizon and you ask, what do they see? So what I want to do is basically try to make up that story with some microscopic theory of geometry. So what is the microscopic theory? We're going to use the gauge gravity duality, so we're going to find the gauge theory and ask questions in the gauge theory and see if we can do those identifications of a horizon and whether there's drama or no drama when you reach it, and this type of questions. So there's a lot of ways in which you could use the gauge theory. Since I say numerical, that means I'm going to do a simulation. I could try to put n equal 4 Yang-Mills on a lattice and do it with that one. But we know a lot of gauge gravity duality examples. And because of the stuff I've been working with in the past, technical reasons, the simplest black hole that I actually know how to build is you start with a BFSS matrix model black holes. And this is ideal for simulations. Part of the reason is that there's a finite number of degrees of freedom in matrices. So if you try to do classical simulations with this thing, you don't have a UV catastrophe problem, which happens for all other field theories. So this is basically the reason that we can do calculations here. Let me remind you what the BFSS matrix model is. So B, S, and S are here, and Fischer, which was my advisor, is not. But I don't need to explain to them what it is. But for the rest, if you haven't heard about it, basically it's n equal 4 or 9 plus 1 dimensional super Yang-Mills, dimensionally reduced to 0 plus 1 dimensions. The coupling constant is dimension full. So when you define this BFSS matrix model, you try to take a limit of strong coupling. And what that means is that the energies that you consider have a particular scaling with n. And with this coupling, that gives you a sweet spot where the BFSS matrix model actually resides. So ideally, we would go to strong coupling. The finite n version of this, so in BFSS, n was taken to infinity. The finite n version of this is a DLCQ description of M theory on the light cone. So finite n is OK. We don't have to take n all the way to infinity to do calculations. There's 9 dynamical matrices, so the x's, there's 9 of them. And there's one matrix constraint, which is indicated by the fact that we have gauge covariant derivatives. And the constraint is basically the statement that we have a gauge theory and not just random dynamical theory.
David?
I'm going to do it in a classical theory, so G doesn't matter in the classical limit. So that's a very hot configuration. So let me be more precise about this. Right? I get to choose the temperature of my black hole, so I can be anywhere. So let's get to that. That's answered by the next slide. So what do we know about these zero brane throats? There was the Horowitz-Strominger type construction of the metrics associated to DP branes. If you take actually the D0 brane one, you have an 8-sphere around the D0 brane configuration. You have these harmonic forms or these kind of prefactors. And if you just take the zero temperature one, what you find is that the integral between 0 and any R0 of, in this case, h to the 1/4, which is the distance along the radial direction, which is infinity. So that gives you a long throat. That's the statement that we have a long throat. And this is infinity for p less than or equal to 3, and h has a particular form that depends on which DP brane we're dealing with. For p less than or equal to 2, or for p less than 3, the effective curvature of this long throat goes to 0 near r equal to 0. So that is well described by gravity and supergravity. When r gets bigger, the dilaton runs and the string or the curvature gets corrected, so it becomes more stringy. So the UV is stringy, and then a hot black hole, which is the one that will be described by classical mechanics in the correspondence limit, will be one where r is big, and therefore you're in the UV regime rather than in the infrared regime. If you agree with me that a hot black hole better have some qualitative properties of a cold black hole, even if the hot black hole well, it's bigger than the small black hole, and the small black hole we think has a horizon and all of these other properties. Maybe the hot black hole has some of that memory, and quantum corrections hopefully will not destroy that immediately if we understand a little bit of what happens. So unless everything is very finely tuned, they wouldn't be destroyed immediately by quantum corrections. Okay, so what's the idea? We're going to take a hot black hole, meaning we're going to do classical simulations on the matrix model. I'm not going to show you the movies of the time dependence of this stuff. What I'm really going to tell you is what do we actually do. We basically put a random. Yes.
If you're in the classical limit of matrix theory, aren't you very far from classical supergravity?
Yes, we are somewhat far from a classical supergravity limit. But it is a hot black hole which is bigger and has more entropy than a small black hole. Wait a minute. So we'll get to the punchline at the end. And for the time being, I just want to give you the data that is obtained. And I'm going to tell you that if all goes well, we can extrapolate a little bit. Tom.
Are you trying to describe the zero brane black hole in two-way string theory, or are you trying to describe 11-dimensional?
The two-way black hole in string theory. Yeah.
So the asymptotic region is still there.
Eventually, yes.
So you're not living in this throat, is that what you're
We'll get to identifying what the throat is in a bit. For the time being, just let me tell you what we actually do. I'll tell you which number, how we can define various regions of the geometry. And then after that, we can debate about how accurate this describes a true black hole as opposed to this very stringy hot one. So, right. So basically, it's hot in the sense that string corrections are very strong. It's big, much bigger than a cold black hole. So this is the limit in classic and quantum mechanics, where you go to very high temperatures. All quantum numbers are very highly occupied, and then quantum statistical mechanics is very well approximated by classical statistical mechanics.
So why is that, if it's a large black hole, why isn't there a weaker geometry that you can function out of the geometry?
Because the dilaton grows as you go towards the UV, so stringy corrections become very strong.
So you are staying with this. So you already took the near horizon.
No. I just have the matrix model. I'll describe what the near horizon limit is, because so let me tell you what's the process. We basically put it on a computer, we let it thermalize, and then we pick a random configuration, and then we ask questions at different values of n, and we see if we get some sort of scaling limit or not. Yes?
So in your limit, if I took one of the eigenvalues and made it very large, so I want to have, you have a very hot configuration
Yes.
I'm not sure exactly how you define this, but you have a very hot configuration of the n minus n, 1 by n minus 1 submatrix, and then the other eigenvalue. If I make that large enough,
Yes.
Does it move around? I'm wondering if there's not just some linear potential that gets generated for that. Is there any way that you could see this sort of classical?
Let me get to that, because if you include the fermions, then it's okay. If you're just doing classical physics, that can describe the core, and then you can try to understand the other guy with the bosons and the fermions treated quantum mechanically.
The one loop potential.
Right. So that, in principle, for an asymptotic guy is well defined. The question is, if you bring it nearby, what happens? Right. So we want to throw someone into a black hole, so we don't really want to ask questions about asymptotics. We know how to do those calculations. And those are weakly coupled dynamics. Yes, but you have to bear with me. So let me tell you what putting it on a computer looks like. It's basically a dirty factory that spits out matrices. Okay? And then you watch for some signal that the thing has thermalized. And then we have tests of that. One of them is that the eigenvalue distributions of a single matrix start becoming like a random matrix. Turns out to be very well modeled by the traceless Gaussian unitary ensemble for a single one of the matrices. But the thing is that if I give you one matrix, I really haven't told you how the configuration is, whether it's very non-commuting or not, and actually where is it located, because that just gives me a one-dimensional slice of the object. We in some sense want to see it in 9 + 1 dimensions. So what we simulate is basically the classical dynamics of BFSS. And that's appropriate for a very hot regime. If you go very hot, the fermions don't matter because they're always at half occupation, and therefore the expectation value that they contribute to the energy is exactly 0. It's a half h bar omega plus minus a half h bar omega summed over 2, because basically the temperature is so high that everything gets occupied halfway. So we did that a while ago. This was done with Curtis Asplund and my current student, Eric Jankowski and Diego Trancanelli. And as I said, this is appropriate for hot, stringy black holes. And then my claim is that some qualitative aspects should be correct. And then we can debate about that once I show you the rest. So this is the real question. Once you have a typical matrix configuration, which just pull at some time after everything has thermalized, we pick one guy from the ensemble, and it should be typical. This is large N. So they should all more or less look the same if we ask the right type of questions. So the big question is, if you have that configuration, how do you probe it geometrically? So this is what we usually do in string theory. We add an extra D0 brane probe that we use to scan off shell. Basically, we can put it wherever we want to. We don't necessarily let it evolve. And we ask an instantaneous question about what that D0 brane sees. Okay? Now remember that the D0 brane probe lives in a flat R9 geometry, so we can ask questions about the probe and locate the information relative to this flat geometry. So I can color R9 with numbers, and then based on that information, I can tell you this place is more interesting than this other one. Okay, so I can basically talk about location in this R9. Still with me, Lenny? Or? I add a probe. I add an extra column and row, and I'm taking an instantaneous picture of that thing. So I'm freezing it at an instant in time. No, at this point it's frozen. I get to pick it. I get to put it wherever I want to, and I am going to ask location-specific questions by asking, what does that D brane probe see when I just add it in? Yes, Gary.
Eva gave a talk in which she was talking about D brane probes, and there was lots of debate or discussion, objections to identifying a point in the geometry with the actual eigenvalue. Are those objections or discussions relevant here in this D0 brane case?
It's relevant, but as I said, we're coloring things relative to the R9 probe space. So we can say this location is more interesting than this one. This one is far, this one is near to something. And I'm going to be more specific about what that is. So for the time being, you just have a configuration, you add a probe, and then you ask, what does the probe see if everything was flat, as if nothing was there, and we're just...
The probe is static, is that right?
It's instantaneously static. So I really take an instant of time and
It's stripped out of fixed position.
yeah, I do everything at a fixed time. And
My question is, when you think about it as a static object hovering somewhere,
I think of it as an object that I add, which is this extra column and row, that I can pick its location wherever I want to, and ask a question about the effective dynamics of that probe very near t equals 0. So I pick my time slice, I freeze my configuration, I ask questions about that probe at that instant of time, and what's the effective dynamics that that probe sees. And then we can either choose to let it run and fall into the black hole later, or we can, in some sense, just ask, how do the different positions see different dynamics?
well, the only thing I'm asking is, you expect two different answers, if the thing is falling into a black hole or if it's being held.
So for the time being, I'm holding it.
Okay.
If I understand correctly, what you're doing is you're simulating with n eigenvalues,
Yes.
and then after you're done the thermalization, you take that configuration, you put it in an n+1 dimensional matrix
Yes.
As a block, and then he was going to ask questions about this new matrix.
Yes.
No. What's the interpretation?
Well, this is what I'm doing to actually get location information. So my purpose is, I know what R9 is. It's the moduli space of the zero brane. So I'm going to try to ask information relative to this thing, which we all probably agree is geometric still. So I'm going to try to color the geometry with information that I can measure. And then the question is, what do I do with this thing in the various regions?
So, I mean, in the other example, we were at very low supersymmetry breaking scale. There was all sorts of evidence for the geometric description of the bulk using the eigenvalue because of that. So here you're talking about very high temperature.
Yeah, but
Much
I can
further
also put
from-
this thing so far away that the temperature doesn't activate any
Okay,
of
so
the
we're sorry,
off-diagonal
that's
groups.
your answer. Okay.
So yeah, depending on where I am.
But maybe Gary had other arguments in mind. I'm not sure what you had in mind exactly.
So the first thing that you might want to ask is, well, how far are we from whatever this configuration is? So how far is the configuration from where I'm at? So the way we do it is basically we compute the masses of the off-diagonal strings in this configuration. And then the smallest such string, the shortest one, will be called the distance. So this is a distance which is measured in some sense by looking at the spectrum of these off-diagonal strings. And to the extent that in classical theory, a string, the lowest lying string is actually the shortest path going from a point to the configuration, this lets me define a distance. So if the distance is 0, I know that I'm on top of the object. And if the distance is way bigger than 0, then I know I'm far. So this is what I'm going to do. And it's better with fermions. And this is, again, the statement that if you take d branes of various dimensions and you intersect them, usually you get fermion zero modes at their intersection. So being on top of something can be better tracked by fermions. With bosons, you get tachyons, not exactly where you're in, or you might not get a tachyon at all. So the fermions do a little bit better job in geometry. So what we do is we take these off-diagonal strings, we look at their fermionic spectrum, and then we calculate their spectrum of energies by looking at the instantaneous Hamiltonian for that particular configuration. So again, this is a well-defined mathematical procedure to extract a number from a configuration and a position. So let me show you what that effective Hamiltonian looks like. You take your matrix configuration that you have, you shift it by something proportional to the identity, which is the position of the probe. So this gives you 9x matrices, which are centered around the probe now rather than randomly. And now you tensor with gamma matrices. These are the 9-dimensional gamma matrices. And this is actually the effective Hamiltonian for the fermionic strings that start at the d0 brane probe and end on the configuration. For the ones that go backwards, it's the adjoint of this object. So the x's are self-adjoint. as matrices, but when you take adjoints or when you take transposes and stuff like that, you have to be a little bit careful with the configuration. So this is the effective Hamiltonian. This is computed from the BFSS matrix model by looking at the fermions. So this effective Hamiltonian will have eigenvalues. Some will be positive, some will be negative. They are fermions, so negative eigenvalues are not a problem. Negative eigenvalue is interpreted as a lowering operator, and a positive eigenvalue is interpreted as a raising operator. And then we just take the absolute value of these eigenvalues, and then we basically get the energies of these fermions. And then we take the minimal one, and that's the distance. So we were doing this with three-dimensional gamma matrices with Eric Jankowski about a year ago, and then that had nice properties. But now let me show you how these things actually look like. Yes?
Just a naive question, if we're really highly thermal, then does the string really track the shortest distance?
So, as I said, this is a definition of spectral distance. It is something that can, if it's 0, then you're on top of the object. If it's different than 0, then you're far away, and asymptotically far away, it does track the distance. Again, this is a number that one can attach to a position. We're going to call it distance because, well, you could call it the energy, but it's something that tells you a notion of distance. It might not be the mathematical distance, geodesic length, but it is something that we will measure. It is a measure of distance. In the same way that when you take a D-brane near a black hole and you let the string fall, that gives you some conversion, some map between distance and energy. And what we know is that when we take something farther from the black hole, the energy goes up. So
of course, if the string is doing all kinds of wiggles,
yeah, but the shortest one usually goes straight. Again, this is a semi-classical statement. So the claim is we do this, we have a configuration, and now we can scan over parameter. I basically built something that was spherically symmetric, and then scanning in every direction going through the center is roughly the same. But let me show you how that actually looks like. So this is what it looks like. So what you have to remember is that these gamma matrices are 16 by 16 matrices. So if you have something like matrices of size 47 times 47, you don't get 47 eigenvalues, you get 47 times 16 eigenvalues, so you get a lot of eigenvalues. The eigenvalues show quite a lot of regularity. So asymptotically, they do whatever they do. They come down to a region, and then they go out again. So the x-axis is the x position of the probe. The y-axis is the energy. And then this is actually for all of the possible fermion eigenvalues of that instantaneous Hamiltonian. So if I take the distance would be the value of this energy over here, the lowest still over here, or this one over here in the bottom. They're pretty similar in most of the places. Well, the eigenvalues of the matrix change because, let me go back. This is built by constants times gamma matrices. Constants times gamma matrices don't commute with x's times gamma matrices because the gamma matrices don't commute with each other. So this basically means that as I move little x, the eigenvalues have a trajectory. Yes? There shouldn't be any crossings if this is a somewhat generic n-by-n matrix. They shouldn't if, as I said, eigenvalues repel each other for random matrices. Is one of the checks that you would have thermalization. If there's too many eigenvalue crossings, then actually it suggests that there's something integral going on. The eigenvalues repel each other except on a set of codimension 3. So the statement is that they typically don't cross each other. So as I said, this is what you get. Now there's these lines over here. I'll tell you what those lines are in a second. They're actually the size of the X matrix. So if I take that X matrix, the one over which I'm tracing over here, and I take the maximum and the minimum eigenvalue, they're going to be located here and here. So this region over here is inside the matrix as far as location-specific concerns are. The eigenvalues of the matrices also give me some type of information location. And the claim is that this region over here is inside the matrix, and that there's, in some sense, some region from here to here where the distance is still greater than 0 by this fermionic measure. Okay. The second thing I can show you is that the spectrum becomes essentially gapless in this region. Everything goes down to 0, and then you go near this region, and it seems like the effective distance inside here is 0, so that suggests that you have this 9-dimensional ball of stuff that's kind of located over here, and that if I get here, I notice that these fermions become gapless. This is still a robust calculation with all the exprovisos I gave at the beginning. This is all mathematically correct. So what I can say is that if I were to do effective field theory for the probe in this region, the effective field theory breaks down in the sense that there's some degrees of freedom that I would want to integrate out, but I can't because they're technically massless. And there's a lot of them. So if these off-diagonal fermion modes, I cannot integrate them out. They're gapless, so they can get excited very easily. So if there's some thermal something or other, I should notice immediately that these fermionic strings are getting created and excited thermally. Okay? So now what I'm going to do is I'm going to take my probe and put it right in the center of that soup and ask questions about, okay, how many of these strings are there that I have to worry about? Okay? So if I fix the position of the probe inside the gapless region, I can define something like a dimension. Basically, it's the number of states near energy equal to 0. So obviously, I cannot have a large number of states at energy equal to 0 because all the eigenvalues were repelling each other. So what I really have is a band near energy equal to 0. And the thing that I can ask is, how does the number density of states change with the energy? And it usually grows like some power law. And then that defines this kind of critical exponent gamma, which I'm going to call the spectral dimension. So why can I call this a spectral dimension? Because you can think of dNdE as something that will measure energy, that will measure degrees of freedom in a quantum field theory of some dimension gamma. So gamma is the number of space dimensions. And therefore, the density of states per unit energy for single quanta should go like e to the gamma minus 1. So in a 1 plus 1 dimensional field theory, the density of states per unit energy is constant. That's the number of fermion oscillators in conformal field theory. If you go to a 2-dimensional field theory, this has to do with the asymptotic growth of states of the eigenvalues of typical Laplacians. So this number over here, which characterizes the dimension, is something that is usually used to define a dimension. So this has the same density of degrees of freedom as a field theory in gamma plus 1 dimensions. And if you had a gas of the 0 branes, energy is a substitute for distance, so dNdD or dr should go like r to the gamma minus 1, which is in some sense the embedding space dimension of a gas of the 0 branes, which in this case will be gamma equal 9. So if E is equal to r, then I can basically count energy by counting distance. And then if I'm in the center of a configuration, the fact that the measure in spherical coordinates has an r to the 8th from the sphere would tell you that this density of states grows like some power of r. And again, this is in the window of small energy. So we throw most of the heavy states away. We're asking whether I can make sense of effective field theory, yes or no.
So there is a subtlety with this kind of thing, or so you can ask what the off-diagonal modes do to the effective theory of the probe if you tried to take it seriously.
Yes.
And there is this factor of n or lambda that enhances the virtual effects of those off-diagonal matrix elements. In the DBI action, the correction scale like lambda b squared over r to the whatever, depending on the dimension. Whereas the non-adiabatic production of the off-diagonal modes is controlled just by v over r sorts of ratios. So there is a regime where it's safe to integrate them out because they aren't produced
Yes.
at large lambda.
Yeah. Just let me let me finish here, and then we can really debate.
This is just a clear thing, and it might help you, is what I'm saying.
Yeah, so I agree completely with that. But there's this region where they're truly gapless, where you really can't integrate them out in any sense whatsoever. If there's a gap, if the fermions are massive, those factors of n of integrating out, we agree completely. In the gapless region, the number of gapless modes that are accessible to me because I'm at finite temperature, well, it has some dependence on n, which is not, it doesn't grow like n, exactly. It's a slightly different number. Yeah. So let me tell you what the spectral dimension of the inside is. The spectral dimension of the inside is 1. So you look at the list of eigenvalues for a fixed position. You just plot them. This is eigenvalue number. This is energy. And you see that it goes like a straight line. So the effective spectral dimension of this thing is 1. So what you have to understand is that having low spectral dimension means that roughly the number of nearby centers where the strings can end is high, because for the NDE, which goes like e to the gamma minus 1, if gamma is of order 1, then there's a lot of guys near 0. Whereas if gamma is a large number, the fact that this is a power of e, that means that near equal to 0, there's very few guys. So the way you're supposed to read this number is that the infrared is very enhanced. There's a lot more infrared degrees of freedom than one would have naively thought if you just compare the system to a gas of the 0 branes in the same position. So as I said, a gas of the 0 branes, which is just centers for string ends, will have spectral dimension 9. If I take a fuzzy sphere and I park myself exactly on the fuzzy sphere, where one of the eigenvalues is strictly 0, you can show that it has spectral dimension 2, and that's just the quantization of Landau levels on a sphere. So the claim is that when you have a fuzzy sphere, the commutators, yeah, they're non-zero, but they're really suppressed by 1 over n relative to the typical size of commutators of random matrices. So they're really very commuting still. Yes, Gary? It's 0 because there's nothing near equal to 0. There's nothing, but no. This is a statement about, this is the spectral dimension of a D-brane configuration if you're on top of the D-brane. If you're away from the D-brane, this doesn't make sense. But if you're on top of the D-brane, this measures the dimensionality of the corresponding D-brane, in the sense of how many nearby centers for string ends do I have. Okay? So far away, you just measure distance by these fermion eigenvalues. Asymptotically, you just diagonalize one of the matrices. And then it's the usual D0 brane story that the eigenvalues indicate positions. But if we do it this other way, the claim is that for very non-commuting configurations, they behave very different than ordinary gases of D0 branes, or gases of D branes in general. The IR is much richer. So all of these up to here is technically correct. Now let me start speculating. This is where I'm going to start to be provocative in a serious sense. 1 is different than 9. So 9 is the putative dimension of the ball where the gap is 0, because that's a volume region where I found things are gapless. And the brane that fills this thing has an effective dimension which is 1 and not 9. So this is very weird. So the way one resolves that is you can argue that physics cannot be local in that region, because a local thing with centers that just kind of are fixed, which is our usual description of locality, where we move around and maybe the centers move a little bit, is just not appropriate to describe this qualitative aspect of the dynamics. So if physics cannot be local in that region, now what do we do? And this is where we really start speculating. So I'm going to start calling the gapless region the inside of the black hole. So if I'm outside the horizon and I stretch a string to the black hole, that string has a finite energy. And as I bring it closer and closer to the black hole, the energy goes down. When it becomes massless, I touch the horizon, or I'm inside, because that's one of the things that could happen. At that point, effective field theory breaks down in the sense that the gap becomes smaller than the naive distance on top of everything. You could interpret this as a redshift. Yes?
You're fixing the temperature, right? Your configuration to start with.
Yeah, but this is the classical matrix model, so the temperature can be rescaled by just rescaling the whole configuration size.
But so is there? So there's a natural like Schwarzschild radius, right? So you compare that to what you're following.
Remember, this is a hot stringy black hole. Near the correspondence region, when you compute the entropy as related to the area computed by the radius of the matrix configuration, and you compare it to the entropy that is calculated, they seem to be of the same order of magnitude. There doesn't seem to be a phase transition from a quantum black hole to this classical black hole. Paraphrasing Gary and Joe, when black holes become more and more stringy, they become more and more D-brane-like, and then there seems to be no phase transition between one behavior and the other one, except for orders of limits. So for density of states and for a lot of other questions, it seems to be smooth. So the claim is that if this is a black hole that is bigger than something that was already a black hole, it should still retain a lot of the black hole-ishness of it, because there doesn't seem to be a phase transition.
I was just asking you the scaling, right?
Only at that correspondence point. Once you're in the classical regime, you cannot use the quantum estimate, which is for a cold black hole, which is supergravity. You will need to do supergravity with a lot of alpha prime corrections to actually get the right behavior. So there's one place where you can say quantum mechanics kicks in. That's a particular temperature, and you can compare that temperature. And colder than that, you need to do Monte Carlo and other stuff like that. And hotter than that, you can do classical mechanics. It might be a region. They did both. They did the hot and cold, and they saw no phase transition. It was a smooth curve, and then. So we know what the specific heat is analytically at very high temperatures, and we could match the specific heat that they got in the high temperature regime and bring it down. And when they bring it down with their simulations to low temperatures, the claim is they get the right type of result. So hot is like classical physics. Cold is very quantum. No, they actually really do a Monte Carlo. It's numerical Monte Carlo simulation. The other paper. We'll get to that one in a bit. or we can talk about that other paper in a bit. I believe that if you read Toby's paper, that one, where they integrate out the off-diagonal modes, the effective entropy you should get is of order n, because there's only n degrees of freedom that are doing anything. But the entropy that he gets is n squared times some factor of the two coupling. So it seems wrong to say that the entropy is of order n squared, but there's only n degrees of freedom playing a role. So I think that part of his paper is technically incorrect. It's a very nice calculation, and he gets all the qualitative aspects correct, and I'm very puzzled by it, but I think that one particular statement, that the off-diagonal modes are really not doing anything, is wrong. Okay, so let me show you how this looks if you come from two directions. What you see is the two matrices. They meet here at the center. That's where all the eigenvalue crossings are. This is just to show that x is equal to y, and that basically all of these curves do pretty much the same. And this is the gapless region. So where does the gapless region begin? When you do things numerically, well, things don't exactly cross to zero, or they tell you here it's exactly where things are zero. What you have to say is roughly there's a region here where the gap kind of becomes sufficiently small that you can't really distinguish it from the typical inter-eigenvalue spacing over here. And roughly at that point, that's where I'm saying we should place the horizon, because that's where effective field theory for sure breaks down. Outside, the fermions are still heavy. Sorry, the fermions are heavy, so they're not completely massless. You can integrate them out, but if there's temperature nearby, then the fermions will know that they can communicate with all the degrees of freedom, and they won't have an exact spectrum. They will decay. So when you integrate out the fermions over here, you should start getting imaginary parts and things that we associate with diffusion and other things like that. Okay.
I'm sorry. I was going to ask a related question. I'm confused. I mean, you expect once the things get close enough together, there'll be thermalization, which will sort of which is sort of what you just said. But how can you talk about gapless when that's when thermalization is taking place on some shorter time scale that you think it would wash out? I mean, that you couldn't resolve anything on longer time scales.
So you move the horizon a little bit further. I mean, the thing is that what happens over here is that the gap comes down. When the gap gets sufficiently big, you can integrate them out for sure. Mm-hmm. When the gap gets comparable to the temperature, which depends on h bar, then, well, you place it here or here, you can call that the stretch horizon if you want to. So you have a horizon, you have a stretch horizon.
Right, I guess, I mean, this comes back to my usual issue, which I'll just mention briefly and not dwell on, which is it possible that everything you're seeing is just interactions of the branes with the stretched horizon rather than things that are necessarily interior?
As I said, up to the point where I said that I was introducing speculation, I was being honest. At this point, I'm really speculating as to how we should divide these things into regions. For sure, since the region here is gapless, effective field theory has to break down. Now, the question is, what do we associate that with? Do we associate that with the singularity? Do we associate that with the what? Do we associate it with the singularity? Do we associate it with the horizon? Do we associate it with the first place where effective field theory breaks down? This is the part that we can debate. Now, remember, I did this for a hot black hole. The question is, what could possibly change when I turn on quantum corrections? Well, the spectral dimension could get an h-bar correction, meaning that I deplete a little bit the modes near equal to 0. The other thing that could happen is this thing kind of shrinks a little bit, but the fact that there's a whole region that is gapless cannot just disappear immediately. That would not be a quantum correction. So the claim that there is a gapless region is the claim that this persists even in the strong coupling high quantum regime. That the spectral dimension is different than 9 is something that should also persist in the quantum regime. Now, whether this is the correct interpretation, I'm throwing this out to you guys to in some sense, think about it. Do you want to say something now? I'm going to call this stuff the inside. Now, this is my jab at Joe. The inside region cannot be characterized as no drama. Right? Effective field theory obviously broke down. There's a lot of gapless degrees of freedom that are interacting with a Hopf medium. They're very easily excited. You cannot just sit there and not interact with these degrees of freedom. So I would claim that an observer falling in there could not help but notice that there's a very hot IR full of degrees of freedom. And if you fix the temperature and vary n, which is something you can do in these black holes, the number of such degrees of freedom grows with n in the following form. The number of infrared states with E less than T grows roughly like n to 3/4. I don't know if this number is important, but it's important that it grows with n. So the number of infrared modes that I'm accessing when I make a bigger n black hole grows with n. So there's more and more degrees of freedom I have to worry about. It's not like it's a constant number of degrees of freedom. It really grows.
I think one issue is that it's hard to distinguish this horizon from the singularity when you're at weak coupling, right?
Right.
So because the distance between the two grows with the coupling.
Right.
So if you find something that differs from what you expect, you don't know where it's a singularity or the horizon.
Right. So the claim is that to the extent that a horizon is characterized by effective field theory breaking down, there's a very particular place where we know for sure that effective field theory breaks down. Now, the bosons also can have their effective field theory break down if they become tachyonic or something else, and that could happen at a different place. And if these two are very different from each other, then there might be a horizon and a singularity. But if, we need in some sense some way to think geometrically about these type of configurations. So the final claim is that it's not no drama. It's very dramatic. Things change a lot when you get into this region. So that I claim that this is evidence for the existence of firewalls. Now, if there's some other region that we call the horizon, which is not this region, you have to tell me why does someone get stuck there kind of forever in some from the point of view of the outside observer. The reason why I think it's important to realize this is that in some sense, I claim that matrix theory tells us when things start becoming less than geometry in some definite sense. And this is one of those senses in which the naive notion of dimension changes, so talking about geometry there is probably not right. Now, if you do things like fuzzballs, then you might say, okay, this is what the typical fuzzball state really looks like, but the fuzzballs that people usually build are still kind of geometric in some sense. They claim that there's all these other ones, but they don't have any characterization of them. I'm saying that this is one of the characterizations, that their dimension is in some sense, measured this way is different than the naive dimension than the outside spacetime. Any questions? Yeah.
So if you just take a D-brane probe in a geometry we understand where there's no confusion about black holes, it decouples not because of an energetic argument, but it decouples just because it's a light source, 1 over g times g squared, the usual argument. So in the bulk, there are glue ball states that are light, but nonetheless, there's a good effective theory of the probe.
Yes.
Not for an energetic decoupling reason, but because literally a decoupling region, the coupling is small. So just for that reason, I'm not sure why you can go from a statement that there are light degrees of freedom to a statement that there's no effective geometric description.
Oh, no. The statement is as follows. If you can integrate the off-diagonal modes out, however complicated that integrating out procedure is, then for sure we have a geometry. When you can't integrate those degrees of freedom out, then the question is it because we're at the horizon, or is it because we failed to resum some important part of the dynamics that would tell us that this is really the third region and does something else? It could be either. I'm opting for the one that says that you can't integrate them out because you're in a place that's not geometric any longer. But we need to be able to, in some sense, follow the dynamics.
Yeah, I'm just saying that for ordinary D-brane probes, there's a slightly more subtle reason that you can, define an effective action that's well defined for the probe coordinate that doesn't rely on an energetic decoupling. So that's my technical question here is how would you tell from this sort of analysis how would you exclude that possibility from this sort of analysis?
I can't yet. Part of the reason is that the main reason I think holography is so hard is we don't really understand geometry sufficiently well to answer this question sharply. And this is where we need to poke at. Hopefully, one of these days, someone will actually figure out how to understand geometry sufficiently well that we don't need to build all this scaffolding to try to figure out, well, maybe the horizon is here and stuff like that. The point is that generically, we can still talk about geometry if we had a probe, if we understand a little bit of what the probe effective action is. I think that we all agree with that. The question that's really important is where in, let's say, configuration space are we really allowed to separate the probe from the rest of the dynamics and integrate the other dynamics out in such a way that we can isolate it? See, I don't know of any argument of integrating out degrees of freedom that doesn't rely on energetics, so I'm a little bit confused by that. I think that there's some things that are one over n, that some things just interact very weakly with a bath, but that usually requires that you have a thermos, something that kind of prevents you from just populating a whole bunch of degrees of freedom that are there. Sure. Yes. We don't disagree. There's still the question of what happens when all these degrees of freedom are actually gapless. And I'm not sure that we can actually still make this claim that the non-adiabatic modes kind of get overwhelmed by these other corrections.
David?
Yes?
I just don't see how any kind of calculation of this type could be used as evidence either for or against the existence of firewalls. So the existence of firewalls has to do with the following question. You have a rather precisely defined place that you call the stretched horizon. A trajectory with some detector on it crosses that place. You have a black hole whose Schwarzschild radius is much, much bigger than the Planck scale.
Yes.
And does something dramatic happen in a microscopic time scale not related to the Schwarzschild radius or only on time scales of order the Schwarzschild radius? Because we all know that you're going to hit the singularity in a time scale of order the Schwarzschild radius.
Right.
So everybody expects drama, whether there's a firewall or not.
Sure.
Trajectories that go into the black hole. And if you don't have this very precise definition of what the stretched horizon is, I don't see how you can even talk about the question.
So at the beginning I said that I was going to be provocative. And this is part of the provocation, is that I'm asking you to, in some sense, think for a minute whether a definition of a horizon given like this, that kind of excises out some region and replaces it by something which is technically non-geometric, is a good definition of a horizon or a stretched horizon. It's something that in some sense will tell me that you know, where my computer code will break down if I do naive things. And if I throw someone in and you know, we take bets of whether they come out on the other side or not, most people would not go into this region to test it. Many.
I'm confused by conflicting claims. Your claim is that you can detect the interior of a black hole in the gauge theory? Joe, your claim is you can't?
Yes. Well,
yes.
Can't. That you can't be sure that you're seeing the inside, and that you're not seeing that you're not seeing, in fact, something which is on the outside.
So I can't be sure of that either. The claim is that this is an interpretation tacked on to some hard numerical facts. This I can be really confident of, that one is different than 9. In the sense that the spectral dimension that I measure is completely different than the one where I replace the object by a gas of the zero branes, and where I just measure the distances to the centers of the zero branes, and I understand the density of those states. So the claim is that the infrared that I see by doing this calculation is a lot richer than the naive gas of the zero brane dynamics. Now, is that enough to claim that there's a firewall? What I claim is that it's enough to show us that we really don't understand geometry at all, to the extent that maybe we can do it.
So actually, I don't want to dwell on this too much, but if you took instead of the eigenvalues, if you formed sort of all the traces of all the matrices,
yes,
that would contain the same information, right?
Yeah, but it's a very.
But we know that is boundary information. Well, we know in ADS that that's boundary information because those are the supergravity fields.
Yes.
So those
actually, could you let me finish and then. And so if you form the trace, if you package that same information in the traces, yes, you would know it was exterior information. So this that's
okay.
That's
so
yeah.
Let's go there. At finite 10, I would agree completely with you that both of these things contain exactly the same information. Eventually, there will be constraints between all these traces. I can specify matrix configuration completely by evaluating enough traces in the UV, and that requires of order 9n squared such traces before I can, in some sense, construct the matrix configuration given the information. Now take n to infinity and keep the number of traces that you're allowed to measure finite. Then it's not true that these will contain the same information as that. This is a different type of measure. Eigenvalues are related to determinants. The determinant is the trace of a log. The trace of a log of a matrix is not something which is, let's say, finite number of traces in the usual sense. Because it depends on a parameter, and when the parameter goes inside the spectrum of the thing, it's not asymptotic information any longer. I need to worry about branch cuts and all kinds of stuff like that.
So my question about this is just very simple. I explained it in my talk. They're gravity waves, and these are... So there are gravity waves, and then there are things like deep-probe positions.
Yes.
These are independent degrees of freedom.
Right.
So the gravity waves are captured by what was just discussed, the chiral operators, and they're smeared.
Yes.
The probe positions are independent of that.
Yes.
Okay.
Okay, I think Gary just reminded me we have 2 more talks, and so we should move on to Mark. I should make Gary session chair.